and welcome to the Kawashi Cyberseminars. My name is Anika, and I will be your coordinator for today. At this time, all participants are in listen-only mode. We will be facilitating a question-and-answer session towards the end of this conference. If at any time during the call you require assistance, please press star followed by 0, and a coordinator will be happy to assist you. As a reminder, this conference is being recorded for replay purposes. I would now like to turn the presentation over to your host for today's call, Mr. John Duncan. Please proceed.
Thank you. Welcome, everyone. Today is our third vision paper cyber seminar that will be presented by Geoff Thyne of School of Mines. So just the typical recap here and introduction for those of you who haven't participated before. This is the third semester we've been doing this series through our education and outreach program. If you have any problems today, feel free to send me a chat or other participants as well. That's done using the chat box in the lower right-hand side of the screen. I'm always wanting to get feedback on these, how your service was. If you have any thoughts on how this could be done better, please let me know. And that can be done by sending me an email to commanager@kawashi.org. If at any time today you have any problems, this presentation can be downloaded from our website, www.kawashi.org, and you can follow the Cyber Seminar link to get to Geoff's presentation. Just to plug the next few Cyber Seminars coming up, the next one will actually be next Tuesday on intensively managed landscapes. That's going to be given by Bill Simpkins of Iowa State University. Then there's also one on Thursday of next week on eco-hydrology of semi-arid environments, and that's by Brett Newman and his team, Brent at Los Alamos National Lab. All of this information is on our website, as are links to discussion forums, which is something new that we're trying this year. So if you have any questions at the end of today's talk, after we wrap up, please feel free to use that. That is linked off of our website as well. So with that, I'd like to go ahead and introduce Geoff. I actually had the pleasure of meeting Geoff and his group this summer out of one of their meetings in Breckenridge. They're a great group and a very diverse group with a very broad background, and I think it's going to work great in such an interdisciplinary effort as these vision papers. Geoff got his bachelor's in chemistry and zoology, actually, then a master's degree in oceanography, and finally a PhD in geology from the University of Wyoming. Geoff's research interests focus on water and rock interactions, especially on the interactions of biological, chemical, and physical factors. So it's with this very diverse background that I proudly produced Geoff Thyne from Colorado School of Mines to talk to you about a framework for interdisciplinary watershed research. Geoff, I think you have control now?
I think I do. Thank you very much, John. I'd like to welcome everybody today to the seminar and thank John for that kind introduction. Hopefully all of you can see the title slide up, and I have a list on my board of all the people that are in fact listening in, or at least logged in, and it's a pretty intimidating and diverse group. What we tried to do and was interpret what Rick and John, as they said, they came and visited us at our first meeting, what they wanted, and our own interpretation, particularly dealing with scaling and scaling issues. And I'm going to say right up front that none of us are experts in scaling. I think we're like most people out there, that is that we, in some degree, in our normal work, but we're not, most of us are not particularly, that's our area of expertise. So our basic premise was that we, as a diverse group of people, semi-knowledgeable, would look into the problem and try and get an overview that might be helpful for so many of us that are working in hydrologic sciences. I'd like to introduce my co-authors here in the next slide. Wendy Gordon, who is now Water Planning Coordinator at Texas Parks and Wildlife in Austin, Texas. Kyle Murray and Adrian Boudreau, who are in the Department of Earth and Environmental Science at UT San Antonio, and John McCrae, who's in the Hydrology Program, Environmental Science and Engineering Division here at Colorado School of Mines. And the picture is us marching across We did choose Citizen Ridge. You may all envy me for that. And we thank Kawasi, of course, for supporting us in that endeavor. And one of the things in the house was this collection of hats, Oriental hats for the most part on the wall. And so in a moment of craziness, we took our picture with them. And I think that captures one of the things that we represent, which is we have a very broad background. You can see a kind of laundry list there of all the undergraduate and graduate majors, that is education and training, that we've had. So we tended to approach this problem from the point of view of we know some things based on our disciplines, but our first task was to review the literature from approximately the last 5 years in particular to get a feeling of what people have been doing relating scaling issues in hydrology. And in the paper that will accompany this eventually, that I, in a matter of a week in the library and confining myself to the major hydrologic journals like Hydrologic Processes or Journal of Hydrology, found over 100 references in recent papers that were dealing with scaling issues. And I'll tell you right now, that was pretty intimidating. So we tried to cut our objectives down to a manageable bite-sized chunks, if you will, and realized none of us would become experts in the specific techniques of scaling, but rather we were driven by the Kawasi vision of these HOs, these hydrologic observatories that will be established. And so our objectives would propose an approach to the scaling problems associated with quantitative watershed modeling within the context of these hydrologic observatories. And our vision, if it might be a bit strong of a word for vision, but at least we could imagine that we would be going and working in one of these hydrologic observatories. And since most of us are interested in quantitative watershed modeling, what would we need and how would we approach this? We decided the approach should be applicable over the next 10 to 15 years approximately. It should be able to accommodate multidisciplinary studies. And we weren't really looking to invent new scaling techniques. We were looking to try and bring together what's been done and say what would be a practical and objective approach. So the first thing was to define what are these future watershed models going to be like? What are the goals? And this is a rather broad statement. But we decided the successful model will have to address the relevant societal issues. And right now, this is a bit of a laundry list, and there are others, but surface discharge rates, that is how much water, vulnerability in the watershed to various types of contamination, and transport of contaminants within the watershed, and the sustainability of those water resources, both quality and quantity, both within the watershed, many of which are undergoing a lot of development, and the export that goes to the downstream users. And of course, you know, what you'd really hope is that these models we create someday in the future would be able to answer the questions for the decision makers, for the public, and for our elected representatives, in order to make intelligent decisions and manage these resources down the road. What's the problem, though? Well, one problem, and that's the scaling problem, is most of us who work in this field make our observations at much smaller scales than the watershed. Here at Colorado School of Mines, for instance, we're working on an adjacent watershed, which I'll show an example of at the end of the presentation, the Turkey Creek watershed. It's about 47 square miles, tractable, if you will, size for a watershed. And we had the luxury of having the USGS and the Colorado Geologic Survey having done a study in 1975 and then another one in 1998 and 2001 where they sampled up to 150 surface and groundwater sites. So we had water quality data, water level, stream flows, and I would call that a fairly highly instrumented typical watershed. Not an experimental watershed, but a generally well-run watershed where there was a lot of data. There's been a lot of growth in that particular watershed. So in addition to this academic data, if you will, there were local water agencies or groups that had monitored their water quality and production, that is water levels in their wells and how often wells went dry for a while. And that was also valuable information. But we realized very quickly that no matter how intensive an effort we made as academics to study a particular reach or a particular area of that watershed, our observations were always much smaller than the whole watershed. So we had to, in effect, scale up those observations. And when people started talking about long-term predictions, what will happen in the next 5, 10, 50, 100 years, we really felt we were reaching quite a distance and maybe getting a little over our heads. So thus, this whole idea of scale was very intriguing to us because it was, well, somebody else has already done this, so we can just take their stuff and use that. So in effect, what we really found was the effective scale, if you will, was which mathematical formulation do we use? Do we use a small scale formulation that we understand very well based on first principles? And then when we try and scale it up, well, gee, it didn't work too well, or that became a problem. So we felt if you can't predict the watershed response to changes in input because of data from different scales, the obvious answer was to get all the data at the same scale, which of course is a little bit easier said than done, or at least scales as similar as possible, and that minimizing the change of scale issues, if you will. Again, a practical type of engineering approach. So we made some assumptions when we set off on this task, having defined it a little better now. And we said things like the future trends or trend for these models will be the Earth system approach. That is, it integrates multidisciplinary data, hydrologic data, biological, geochemical, geomorphological, ecological, all into a single model in watershed models, that this is the approach and the way we need to go. We recognize that there are two fundamental differences in approaching modeling a watershed. One is that fundamental physically based model. The other are empirically based models. But we think that both approaches are obviously going to continue, but that all the models will use the basic distributed approach. And I'm not going to go into that in any detail. There was a conference back in 2000 and a special edition, I believe it was the Hydrologic Processes 02, which deals with the distributed approach to watershed modeling. We also felt that the scale of measurements in watersheds are pretty much going to be limited to existing and emerging technologies. And we did a brief review of those existing and emerging technologies. I think the great unknown is going to be remote sensing, but I'll talk a little more in detail about that later. That's something that we hope will feed in and help us, all of us who are doing watershed modeling. However, I want to say that one thing that came out of my review of the literature was the fact that we all work in sub-disciplines. And the first thing that struck me was, well, everybody's, boy, they're really working hard in their sub-discipline, but no one's looking over the fence at the next guy and then down the street at the neighborhood to see how it's all going to come together. And when I say nobody, that's not true. There have been a few articles where people have at least discussed these concepts in the context of someday linking this together. And I like those. We all like them. And we thought, well, you know, this is a good thing to do, but maybe we can find a touchstone or a practical approach to this to start the discussion. So I think the other thing that comes out is the last point. We're going to continue to make point to small catchment scale measurements that have to be scaled up to these model grids that are going to eventually encompass something the size of an HO. We're not all going to go out and learn to do new things. We decided that the framework should try and limit the problems by limiting the degree of scaling up and down. So whatever framework, and at this point I think we had all decided a framework meant in our minds was actually a model grid, at least as a point to envision, and that this model grid should be such that the scale was sufficiently large that scaling down from, say, global climatic models wouldn't be impossible, or scaling up from a point measurement or a laboratory beaker-type experiment wouldn't be impossible either. The framework, we felt, should facilitate merging data from smaller research sites into the much larger HOs. I think most of us have been at least peripherally aware, if not actively involved, in the formulation of what is going to go into an HO and who's going to be awarded an HO, to cut to the real point. And one thing that jumped out at us was, well, if we were doing it, and of course I'll say right now, John, we're not, but if we were doing it, one thing we would be thinking of is, are there existing facilities, that is experimental watersheds, within something that will someday become one of the HOs? And the answer would be, I hope so. I would hope that work wasn't lost, and certainly it would seem to us to be a positive attribute for somebody attempting to build an HO to already have experimental watersheds there. Plus, we realize that most investigators, at best, will only create something the size of an experimental watershed within the HO that's heavily instrumented, where detailed studies are done. So there has to be a way to bridge that gap, because these HOs are going to be quite a bit larger, up to 10,000 square kilometers, which is a huge, order of magnitude, or really 2 orders of magnitude leap from the largest type of experimental setups we have now. This core data issue came up as well. Rick and John came and visited us and made a point of saying one of the keys they believe to success is that the operators of a hydrologic observatory will provide all interested parties, people both affiliated with that organization and outside, with core data. And core data hasn't been defined yet, but in our own minds, core data were the basic measurements, the topographic distribution of vegetation, stream flow, things like that, that we would have. And right away we realized from our experiences here in Colorado that supplementing that with any other public domain information was really another key element to getting the most out of these hydrologic observatories. And then lastly, based on our experience, we realized that GIS will be a fundamental tool for constructing future watershed models. I think that there are perfect examples of how GIS has worked very well to construct watershed models. However, I also acknowledge the fact there are watershed models that never really use GIS. But looking ahead, I think given the advancing technology and sophistication of, in my case, I'm talking about ArcView and the associated products from Esri, but I think the GIS is going to be the way to go to handle these large amounts of data. So using these assumptions, we moved forward. And we realized there were, basically, in the literature, 2 types of models. The physically based models with rigorous mass and energy constraints, if you will, the real science models, the things we all strive for. Ultimately, we would hope a watershed model would meet a rigorous mass and energy balance constraints. However, most people have moved ahead with conceptual models, which have empirically calibrated lump parameters that enable prediction. However, these models lack the ability to evaluate the fundamental relationships and extend our understanding on a mathematical basis. So it's a bit of a quandary. We don't offer any solutions to the quandary. We think both will continue, and eventually, hopefully, we will find a way to get back to the physically based models. But for now, I think the empirically based models will pretty much dominate the modeling scene for a while. So one thing I wanted to run through here was scale and the fundamentals of scale, because in those 100 papers written in only the last 5 years, the first thing we had to do was learn a good bit of jargon and kind of deconvolute our brains from what we thought we knew to what all these people who know a lot are talking about. And I'm sure a few of you are listening today and wondering what an idiot I am. You know, how come some expert didn't do this? And I hope one of Kawasi's points was to get more common, if you will, researchers involved in this and to get their point of view on scaling. This diagram in front of you, modified from Vogel and Roth, shows the fundamental idea that there's a dependence. That is, as the log of the observer parameter value changes. And we see the typical one, the macroscopic homogeneity, the discrete hierarchy, that is, that there's a repetitive pattern as the scale goes up. A continuous hierarchy where there's an oscillation, if you will, around this central line. And then the concept of fractal, which is fundamentally scale independent on some degree. And it's been argued in a number of these publications, and I have to agree, that when we study a watershed, some processes may be fractal, but some may have a discrete hierarchy. And so right away, the first thing you have to do is decide what type of hierarchy or scale dependence, if you will, your parameter has, because that has a tremendous effect on what technique you're going to use to scale. As an example, I call your attention to the central property, if you will, of the medium. And dispersion is that, if you will, ink drop or contaminant put into a groundwater flow field through a pore, and as it moves through a porous media, it disperses. Part of that dispersion is controlled by diffusion, chemical gradients, but part is a reflection of the differing velocity fields as that mass of groundwater moves through a very complex media with different pore diameters, different travel lengths. It's a fundamental property that, if you will, that's investigated intensely, particularly in contaminant transport. And this diagram shows the scale of measurement versus the longitudinal dispersivity, which is a measure of how much dispersion there is. And what we really notice is right away is they're log scales. And we have, well, you know, if one of my students came to me and put a line through this data, I'd first say, well, it's a log-log relationship, so you're covering up all the details. But more importantly, I'm not sure you can put a line through this data. And so here we have this fundamental property of aquifer material that is very difficult to scale. If you make an observation or you do a tracer test on the scale of, let's say, 10 meters, what's your longitudinal dispersivity? Well, gosh, it's about 100th. Well, about isn't going to get us there. Most of these things are shown to be linear functions from distance to source at scales about 1 to 100 meters. But that's dependent on the heterogeneity, and it can change radically, hence the scatter that we see in this plot. In the end, people have decided, Shlomo Neumann, for instance, wrote a paper in '89, I believe, on this sort of thing, that it's highly nonlinear. Okay, well, that takes care of the simple scaling issue. And it's really difficult to predict at scales, less than a meter or greater than 100 meters. Well, those scales are very important because many of our experiments are small scale, a couple meters, but many of our predictions, particularly in the watershed scale, are going to be over kilometers. And I do note that at least in the contaminant literature, we've been able to predict this reasonably well at the 30-meter scale. And the 30-meter scale turned out to be important to us. A little pre-staging there of where we're going with this. Also I wanted to talk briefly about the approaches people have used to scale, just so we're all on the same page. The approaches that we found in the literature, and scaling, downscaling, and in the literature that's often called aggregation and disaggregation. It took us a while to get that straight. And then there's disaggregation aggregation, which is kind of a combination of the two, fractal scaling, and finally the use of characteristic scales. So I'm just going to briefly talk about the first four so that as they come up later we are all on the same page. Upscaling or aggregation is used when you take the small scale data from an experimental or site scale and you try and scale it up, let's say to a watershed model. So an example would be the dispersive nature of an aquifer material, and I may measure it at a field scale on the order of 10 meters, but when I want to predict what will happen over a 10-kilometer reach of aquifer, I'm stuck with how do I scale up dispersion. Downscaling, the opposite, disaggregation. This is developed to take these large-scale data sets, for instance, the atmospheric circulation models or remote sensing data, where the scale may be hundreds of kilometers, the scale of interest in atmospheric modeling, for instance, and taking that down to the point scale of a rainfall event. So it's the old question of, you call up the meteorologist, he's got NextRad, he's got computer models, and you want to know how much snow, if you live in Colorado, you're going to get in your backyard. Well, it's someplace between 1 foot and 3 foot. Well, that makes a big difference when I'm shoveling. Disaggregation aggregation tries to downscale these catchment size variables, and those would be empirically determined, to point scale, applies a physical model to the downscale data, and then upscales it back up. The idea being here that you're trying in some way to get a physically based model incorporated into your catchment scale process. And by starting with the large scale, coming down and relating that to a physical process and then scaling back up, you're, if you will, ground truthing that empirically based parameter, or forcing it to at least conform to some degree to what we know are the fundamental principles. Finally, the fractal approach has tried to find these fundamental scale invariant relationships in hydrology. I think that we'd all hope that everything is fractal in the world, but it's turned out some things are not fractal. Hopefully they're linear, but unfortunately, generally they're nonlinear but not fractal, or at least we haven't been able to find and prove they're fractal yet. One of those, I guess, holy grails, if you will. So, our framework. What did we want to do? Well, we chose a standard grid size for models that minimizes the upscaling and downscaling. A very simplistic engineering approach, if you will. And in order to choose that standard grid size for our model, or scale for our model, if you will, we considered what data was common to any watershed problem that's already available. And, you know, all that available data, what's it scale at? The example I'm going to talk about today is for spatial scale. You could do the same thing with temporal scaling. That is certainly an issue, but I think the spatial scale issue was one at least all of us were more comfortable with. We could touch it, go out and feel it. We were familiar with our own experiences in studying watersheds. And we decided in the end that geomorphology was the common link to most of the things I'm going to talk about. So let's look at some of the fundamental data that you and I and everybody's going to get when they do a watershed model. This is not an exhaustive list. This is where we started, however. Precipitation types, vegetation, land use, surface water locations, streams, lakes, whatever, impoundments, dams, surface temperature, and the geology. And since we had been trying to construct a watershed model ourselves, we had actually gone out and gotten a lot of this data. And one thing that kind of came out at us, and you notice I have a question mark next to NextRad, because I understand that the data can be gotten at a variety of scales, and I'm still investigating whether I believe 30 meters, and hopefully one of you will chime in on this. But most of these types of data could be at the 30-meter scale. And 30 meters, I want to say right in front, 30 meters is a number worth throwing out for conversation, for discussion, for debate. Some of you may have experiences or knowledge that say, hey, you're an idiot, 30 meters. No, it's 10, it's 5, it's 2, it's 1, it's 200. Love to hear about it. However, for the sake of this discussion, I note that many of these sources of data, and these, by the way, might be considered core data that you'd need to know about your watershed if you were coming to study there. A little plug for core data there, John. But most of these are readily available. The DEMs are online for most people to go download. The StatsGo, Surgo database, which covers soil types throughout the U.S. at different scales, can easily be gotten and digitized to 30 meters. Kyle Murray is quite an expert in this. The Landsat data has been available for years at 10 to 30 meter resolutions for vegetation types, the land use, the surface water, geologic surveys. When we say that, we meant geologic maps, and in addition to domain surveys of other types. Other data that you might use in a ground, I should say a watershed model, would include stream flow, groundwater levels, water quality, ET, obviously, a very fundamental parameter, imports and diversions, very common in developed watersheds, point source discharge, soil moisture, wind, solar radiation, humidity, hydraulic conductivity, porosity. We could all make a list. It would probably be longer. We note, though, that this data is available either through the U.S. Geologic Survey, state geologic surveys or state agencies, county agencies. I put EPA down. EPA is, in my experience, the data is public domain, but you got to know the right person to get it. However, they've got an awful lot of data. And the etc. part is there may be environmental agencies at both the state and local level that have a tremendous amount of information accumulated, generally not analyzed, but it's all there, that you can get hold of. NOAA, National Weather Service, a number of people have well tests for hydraulic conductivity done, privately that they're happy to share with. And again, the resolution here is either a point, which would be, on the order of 10 centimeters to a meter, or someplace under 100 meters. All this data seems to be well under or close to 30-meter scale. So the point sources are being scaled up an order of magnitude or two, and that seems to at least fit the criteria that we don't want to scale too much. We also kind of started kicking around, where do you get more data? Sources such as these contaminant studies, which I don't think academics utilize maybe as much as they could. There's a lot of remote sensing data, and there will be whole talks about that later, so I think we can leave that as just for the moment. And then the scale of experiments and sensors that we all presently use, maybe I should put a question mark here. Can they be adapted to 30 meters, to a 30-meter grid or a 30-meter scale? So I'd like to show you some examples once we picked the 30 meters and started going, how many things can we make fit? Well, it's kind of interesting. Well, contaminant sites, we can understand and measure a lot of these transport processes up to about 50 meters. The data or the wells exist, so we don't have to go out and put a lot more money into drilling a lot of wells. In a lot of these watersheds, hopefully in the HOs, and maybe that should be a criteria for an HO, that there is a lot of existing stuff. And we can investigate fate and transport scales up to about 100 meters. The real challenge above 100 meters is really the cost, not the technology limitations. And I think all the HOs are going to face this. I mean, I'd like NSF to just put another zero behind your budget, John, but I guess that'll be a while. So we think contaminant transport is the general term, but these contaminant sources in watersheds are often point sources. There's data from a lot of these sites that's public domain, housing developments, wastewater pollutants from septic tanks, runoff from construction, air sources, that is deposition from the air, industrial sources, gasoline spills, landfills. All landfills in the country are required to constantly monitor the groundwater around them, both for water quality and elevation. Quite a bit of data there. We note that these transport studies or pollution transport incorporates a number of factors that we as watershed scientists are interested in, as surface reactions, mineralization, dissolution, as you will, of the rocks, and dispersion. These processes are all been studied at the beaker scale, but not really scaled up yet to the watershed, which is something we're going to have to do to have us, we believe, to have a really good watershed scale model. Here's some examples. This is an old dump where they dumped solvents and metal waste in Idaho. Most of us would guess Idaho, yeah, that's probably radioactive, probably near Hanford there. But the point is, most sources are on the order of 100 square meters, maybe to 1 million square meters. You know, that's only 1,000 by 1,000 meters, kilometer by kilometer. That's rare. Most are 10 by 10. So we're in the right scale again. We have point source releases, if you will, we could study. This is maybe a little more typical. Here's a picture from Virginia Beach Amphibious base. This is a study that was done 2 years ago, and you can see the wells there sited quite close together. You could cite a dozen wells in a 30-meter grid and get a real good idea of the spatial heterogeneity and parameterize things you might want to know. Sorry about that. Looks like my slides look a little funny here. Here's perhaps the largest well-studied contaminant plume, Washington State, again associated with the nuclear industry. The scale is large. It's about 2 by 2 kilometers. More than 20 years of study, we see kind of some plumes there, leaving these plants and these disposal sites shown there in red. I apologize, the text is almost unreadable in my version. And yet, after 20 years of study, they're still not really understanding how the plume moved and what sort of thing happened. But when we see that there's an upper and lower scale for these contaminant transport processes, it fits pretty well in our 30-meter scale. Hydraulic conductivity, another critical parameter. Pump tests, which is the common method to study that, really work at scales less than 100 meters, pretty much, except for long-term pump tests. So again, we're around the 30-meter scale. Well logs, which are generally filed by everybody who has to drill a water well with some state agency, can actually have parameters on it that you can use to estimate K. The scale of measurements, well, pretty much between the homes that installed the wells, again, around the 30 meters. And so we felt that this was another case where the 30-meter scale worked well. Now, remote sensing. Topography, which we know very well now from DEMs, easily at the 30-meter scale down to maybe even the 5-meter scale, depending on the type of instrument used. You can use that topography to get to other variables of interest. So this is kind of, again, a list of things that we found where you could take a topographic variable like elevation and get a variable like precipitation from it, which would be a fundamental thing we'd need in a watershed model. Aspect, for instance, can give us incipient solar radiation, hence precipitation, snow accumulation, and melting. These things are underway. These things are being done now. We can see them growing, and we can, in part what we wanted to do was set up a target that everybody could go at in their separate sub-disciplines, hence the 30 meters. Remote sensing, another idea that Kyle Murray came up with, we could actually estimate ET from remote sensing, and he found a couple papers, Anderson et al. In 2003, that showed the spectral reflectance and emittance data measured by the satellite or airborne remote sensing equipment can be used to obtain these parameters. And you note again the resolution, Landsat, Avarice, Aster, ADS-40, certainly 30 meters. 30 meters is resolution. There's a lot of bands of information, particularly in Avarice, which really haven't been fully exploited yet. So I think that's another way to get a lot of this information. So our proposed framework is that the most common scale is 30 meters. Some related data can be obtained at that scale, intermediate between the other scales. A 30-meter grid requires about 11 million cells per layer in a model, which is tractable given the increasing computer speeds and memories. We all buy G5, let's hope. And other related parameters could be measured at the 30-meter scale. At least we think once it's out there, a lot of it could be done. And here's an example. This is a microbial process, something most of us have not incorporated in watershed models yet. There's no data at this scale to date. They're usually studied with these small little samples, a gram to, tenth of a kilogram of soil. And they're generally focused on soil respiration, how much CO2 comes in and out. Usually closed or open chambers. There's various ways to do this. But once we went and did some research, what we found was that people are using automated systems to measure CO2 flux. Here's an example, a point scale, if you will, that can be set up, left to a data logger, and then queried. Or here's under development, is actually a dome to do the same thing. And you note the size of that dome is not 30 meters, yes, but several of them could be set up in a 30-meter scale, or assumably a dome could be scaled up to 30 meters. And things like respiration could be measured on that scale. And that avoids, again, the scaling problem. In theory, if everything's on the same scale, we avoid the scaling problem. So how do you actually do this, briefly, of how you actually perform this once you bring your data together? And so our examples from the small mountain watershed, specifically Turkey Creek Basin here in Jefferson County. You can see in the map it's adjacent to Denver. It's a very area that's undergone a doubling in population. Lots of people like to live up there in their mountain homes. It's a 20-minute drive to downtown Denver. The prices are outrageous if any of you are thinking of moving here, but hey, you know, that's what you pay to live here in the mountains. So there's our watershed, and that's a rough geologic map. So how do you actually go about constructing this kind of model we're proposing at the 30-meter scale? I'm attempting to advance this and show that a 30-meter DEM serves as our base map, and here's the 30-meter DEM. And so, in essence, we would create a grid where we had a value for every 30-meter grid cell, and that is an elevation value. Then we would move forward and add a digitized, a raster image that had been and what this represents is a digitized geologic map that you saw before. And what this allows us to do, in essence, if my figure comes up, is we can make a point-to-point association. For every grid cell, we now have an elevation as well as a geologic value. Is it a gneissic or granitic rock? Is it in a fault zone? Is it a coarse granitic rock? What type of geologic material do we have? So within GIS itself, we are building a database which has a parameter value for every grid cell, starting with the topography, as we said, because we believe that's important. Other types of data can be treated exactly the same way. This is a map representing recharge, amounts of recharge. It was based on a slope aspect elevation algorithm that Dr. Murray created. And the point is that we can also take and digitize this image, and Dr. Murray has written a piece of software that allows us to sample and get a value for recharge for every 30-meter grid cell. And then lastly, other types of data, and in this particular example, a synthetic data. This is a synthetic parameter. This is a map, a color-coded map, where water chemistry, in this case 12 different parameters, have been aggregated by statistical techniques to one parameter, and that one parameter has been kriged to generate a raster image, and this raster image can be imported into GIS and then sampled to give a value between a digital value, exact digital value for every single one of those grid cells. And again, I don't know if this is truly circumventing the scaling issue. I don't believe it is, because there inherent within the production of these values was some aggregation. However, at least we have the ability to create these models. So our conclusions: integrating multidisciplinary data and computer models will clearly be facilitated if we all had a standard grid size to shoot for. Many types of data are already available at this 30-meter grid size. Data from non-traditional sources, contaminant studies in particular, are applicable at this scale. The scale is intermediate, hopefully minimizing scaling from the larger and smaller scales. And measurements for many of these processes of interest, we think, could be made by indirect methods, remote sensing and gathering CO2, that sort of thing. If there was a need, if we all agreed that this 30 meters was a good idea, I think the DRI would be happy to build a 30-meter and test it. And hopefully that's the direction that we're going. And with that, I'll conclude and open up for any questions.
At this time, ladies and gentlemen, if you wish to ask a question, please press star followed by 1 on your touch-tone telephone. If your question has been answered or you wish to withdraw your question, please press star followed by 2. Questions will be taken in the order received. Please press star 1 to begin.
And I say I do have one comment here. 1 or 3 feet of snow, either way it's a ski day. That must be Mike out there at Utah State University.
Well, Geoff, thank you very much for that talk. Very thought-provoking.
Well, thank you, John. I hope that that was our intent, was simply to provoke a little thought and try and find a way forward. I know there are a number of people who have devoted a great deal of time and energy to coming up with scaling algorithms within their subdisciplines. And I really salute all that work that's been done. Our aim was simply to try and step back in a little bigger picture.
Again, ladies and gentlemen, to ask a question, please press star followed by 1. Our first question comes from the line of Praveen Kumar. Please proceed.
Yeah, this is Waylon Ehart at the University of Illinois. You didn't say anything about characterizing uncertainty, which I think would be a very important activity for Kawasi. And it seems to me that whatever you're trying to do at whatever scale, whatever resolution, it's going to take a lot more data collection effort if you really want to try to tie down how much uncertainty there is in the data.
I'd like to say I absolutely agree, and I would hope that one of the literature, one of the themes we saw in the literature was without a common scale to all work toward, everybody is kind of working off in their own compartment, if you will, and working on things like uncertainty. And so I don't think we're going to get as much progress as we could make if we all agreed on the same scale, and then, as you say, made numerous measurements to work on the uncertainty issue on that single scale.
So you're saying that if we are going to characterize uncertainty, it makes it all the more important to be working on the same scale.
Exactly. Okay. Because otherwise, you know, I may say, gee, my uncertainty is really great at this point measurement scale, but when I scale up to the watershed scale, what's my uncertainty now? Was it a linear extrapolation of uncertainty? Is it the same? It becomes, I wouldn't know the answer. Mm-hmm. And people have asked me that actually about water quality predictions, and I'm like going, well, that's a good question.
All right, thanks.
Sure.
There's a couple of comments there. One by David Maidment, who is actually one of the 4 PIs on the Kawasi Hydrologic Information Systems grant, saying that this is very consistent with what the HIS team is working on with what they're calling the digital watershed hydrologic data model and the model shed concept, which Praveen Kumar and others have worked. And someone from Temple, can you see these, Geoff?
Yeah, it said airborne geophysical data can also target the 30-meter resolution, and yeah, I think that's particularly important when we're talking about satellite photos, high-altitude photos, as well as sensors that are flowing. 30 meters seems to be a very tractable target and doable kind of thing for all of these sensor platforms. And I think that's important if we propose a scale that's, going to take another 10 or 15 years work. I don't think that's the way to go. And then I see another one. We should distinguish between scale issues associated with parameters and processes. The scaling issues associated with the two are fundamentally different. Yes, that is quite correct. And our problem in that became, when we discussed that a little bit, was many of the parameters that we measure are actually representations of a number of processes, and versus the process itself that we're studying. And I don't think, oftentimes it's built in and inherent, and it's not explicit when we report our results about this. So I would hope everybody would kind of remind each other, I'm talking about a process, even though I'm measuring this parameter, these processes are inherent in it. And that becomes a difficulty when you're talking about scaling as well. Hence the 100 references in the last 5 years, which I think represent the complexity of this issue.
Our next question comes from the line of Iowa State University. Please proceed.
This is Brian Hornbuckle. Can you hear me?
Yeah, I can, Brian.
I thought you did a great job, and thanks for the presentation. I have one comment. You talked about the data and the resolution of the data, and I agree with what you had there, except for one variable, and that would be evapotranspiration, and I don't think you can measure that at a point. I think you're right that we can produce estimates of evapotranspiration at scales of 30 meters, but the data that we would use to validate those estimations would be hard to get at 30 meters because you have to think about, I'm thinking about egg correlation systems, bone ratio systems, and fundamentally it's that fetch that it could be on the order of a couple hundred meters that's affecting the measurement you make at a point. So I don't think you can call that a point measurement.
Thank you, Brian, for the kind words. What I was thinking of was what we've been doing is either an ET tower or an ET dome, which is a couple feet in diameter. And the dome, at least we felt, you're right, it's not a point, and it's, I guess I should have said a meter. The tower, oh boy, and you're absolutely right in terms of how good a measurement of ET can we really get. And in our particular watershed, we finally just went with, there's just a couple vegetation types. The USGS was kind enough to set up a couple towers in each vegetation type, and then we went out with our little dome and, went around to those vegetation types and see how close our measurements on the ground were compared to their measurements, which were the instrument package was suspended in the air about 10 meters. But hopefully, by proposing this, it might give people in remote sensing a target that is a 30-meter scale, reduce uncertainty, how close can we get? And I honestly believe after all these references and talking to people that, this is going to be a major ongoing effort for the next 10 to 20 years. And it's going to involve a lot of really smart people working hard. And hopefully, if we all could kind of converge on a general goal, it will really facilitate and increase our effectiveness in our work. And I think that's all the comments I've seen to date here on my screen.
There's a follow-up from Temple, but are there any other, just a comment.
Yeah.
Are there any other questions in the queue?
At this time, gentlemen, you have no further questions.
Okay, well, it is almost 4 o'clock, so if there aren't any more questions, we are trying to wrap these up on the hour, given that a lot of people have got to give up their rooms, so their seminar rooms, for the next class coming in. So I guess one last chance for questions.
Again, to ask a question or give a comment, please key *1. We have a follow-up from the line of Praveen Kumar. Please proceed.
Yes, this is Praveen from University of Illinois. I think the presentation was good, but I think there is a complexity of problems that are fundamentally ignored, and I'd like to bring that to the attention. I mean, I think this was a great job perspective. I think when you look at processes which are in a very integrated fashion, when you're looking at hydrologic observation, you are integrating from very small scales to large scale effects. Just because you can model at a 30-meter resolution, or you can interpolate from a core scale data like geologic maps to a 30-meter resolution does not mean that you will be able to assess integrated response at the large scale. And for that matter, vice versa, going from climate influence to very fine scales. There are fundamental assumptions involved. There are fundamental hypotheses that need to be invoked, and I think that was one of my points when I was trying to point out between parameters and processes. The scalings are fundamentally different, and that needs to be brought into this discussion. I think saying that a 30-meter target is a good enough target, I think might be misleading from a hydrologic observatory perspective. Thank you.
And gentlemen, you have no further questions.
I'd like to thank the caller for that comment. That was something we wrestled with considerably, and with a 20-page limit, we eventually had to cut our discussion off. And I will make sure that comment is included in the paper. As I say, This was a basic engineering approach, a first cut by a bunch of non-experts with how we would tackle it. And if we invoke discussion, and if we do find, and I hope we will, that 30 meters may be good for this but not for that, particularly in studying fundamental processes, it may be that we'll have to come back and revisit this entire idea. Move the discussion forward, because the 150 papers that I tried to read, I think would intimidate most anybody. And hopefully, as I say, we just engender discussion, whether it's 30, 10, or maybe we do have to have two separate scales, fundamental scales, for studying processes versus parameters. But I want to thank everybody for listening in, and it's been a unique experience for me. And again, I want to thank Kawasi for funding us for our travel time. It's too bad you guys didn't have money for a stipend too.
Well, Geoff, thanks again. Some very stimulating points have been made, and I encourage you to follow up with these. And it's a really interesting topic, and you guys have taken a stab at this. And I've talked with you a bit about this offline, and know more about where you're coming from, and really appreciate you trying to take this step. And again, I'd like to remind everyone that the point of these cyber seminars is to essentially raise the bar at which the community talks about these types of concepts. And as such, we're providing this discussion forum that you can find linked to our website. And this is an opinion piece. And Geoff and his team have been brave enough to throw the 30 meters out there. I don't think too many people would do that. And I do suspect that that number is going to change depending on what particular process or parameter that you're actually looking at. But I think it's a very important first step in laying out at which parameters and processes can be looked at this scale. And I really encourage all of you interested in this, they're still submitting comments in the chat box there, to use this discussion forum. And really, let's try and further this concept, because it is going to be something that we're going to be wrestling with, and many teams are wrestling with for these hydrologic observatories. I guess not too many people have signed off. Are there any more questions in the queue?
Yep, we have a follow-up from the line of Praveen Kumar.
Yeah, sorry to be bugging you, but I just want to make sure. I mean, I've been working on scale issues for the last 15 years. I've probably read more than 100 papers. And I just hope that Kawasi does not accept 30 meters as a guideline. This problem is way more complex than projected to be solved at a 30-meter issue.
And as you well know, Praveen, we're not going to endorse any scale. That's up to the individual team if they get to this point. But it is something that you and others are working on with the hydrologic information systems concept, with the data model and the digital watershed. And but no, we're not going to endorse any grid size for meals. But
I wonder, Kumar, given, and I do realize how long you've been working on this, and a lot of your work was included. What scale would you, take a stab at?
Well, the issue is, why do you need to pick a scale? I mean, the problems have to be solved at a multitude of scales. I mean, there are issues arising at several different scales, and you find the appropriate scale or interaction between these scales to solve the problem.
And that's also exactly what an integrated system is going to do.
Well, I guess our point of view or thought on this was, I'm trying to conceptualize how you'd actually construct a model, a multi-scale model.
Well, we do that all the time. I mean, there are a variety of ways. The issue becomes, issue is more of what is the scale interaction between these processes? It's a complex process. And, the atmospheric scientists have been doing it, the hydrologists have been doing it. I mean, I think the solution at which certain types of processes are acceptable, but there will be different processes at different scales which are relevant, and that has to be a fundamental recognition in this issue of scale. It's a scaling up, scaling down issue. It's not thinning down a particular scale for all the processes.
I do agree and value that comment. That's what we came into, and so we were in in part what we were trying to do is say that there is a lot of data available at common scale. So as a practical approach, and this may play back to what is the core data provided by an HO. We had to choose something to convey a lot of this information to the researchers, and I believe that's what Kwasi's idea for the HO is. And so that was what we were targeting. We were not trying to say that all processes will be able to be described accurately at the 30-meter scale, rather that all this data is presently available at that scale, and some processes can be measured at that scale appropriately.
Okay, well, I think we're going to have to wrap it up. Folks are leaving, and we should as well. Thank you all for your comments, and Geoff, thank you and your team for all of your hard work. And again, I'm sorry that we have to wrap things up, but I encourage you to use the discussion forum to continue this dialogue. Thank you very much, everybody.
Thank you,
for your
James.
participation in today's conference. This concludes the presentation. You may now disconnect. Good day.
Hey, Geoff, you still there?
Yeah, I am. I was just curious how
One second, gentlemen, while I transfer you into a private room, okay?
Comments? I mean, they're over here in my little box, but I don't.
I could do that.
I don't know how to download them. I mean, I can highlight them, but I can't seem to copy them.
Oh.